All right, now we're going to talk about section 2.3. This section is really not very long, so I don't expect this video will be super long either. We're going to address for the first time the issues of existence and uniqueness of solutions for first order equations. We have this theorem that tells us exactly when we have existence and uniqueness. But before we get to that, I just want to mention that existence and uniqueness are the two biggest questions that you can have for a differential equation. It essentially boils down to, can I guarantee that a solution exists? If you can answer that question with a no, then why are you even trying to solve the differential equation? Maybe you need to find an approximate solution instead. If the answer to that question is yes, then the next question that you should ask is it unique? Is there only one solution, or could other solutions potentially exist? And by the way, what I'm talking about is not just a differential equation in this section, it's an initial value problem. And the initial value problem that we'll talk about is in the form of y prime equals f of some f, where f is some function of x and y. If you're not given a differential equation in that form with y prime by itself on one side of the equation, then before you even look at this theorem, you would rewrite that equation in that form. In other words, isolate y prime on one side of the equation. And then of course we also have an initial condition at x equals x naught. All right, so here is the big theorem. First part of the theorem says if f is continuous, this function f, if that is continuous on an open rectangle, I'll talk about it in a second, what an open rectangle is, then there exists a solution on that open rectangle. So let's define that. So an open rectangle is defined as, let's see, it is a subset of the plane R2 given by the set where let's see, x is between two values a and b, and y is between two values c and d. Notice that I'm only using less than inequalities here. I'm not including the values a, b, c, or d. That is what makes the rectangle open. So think about, compare this to an open interval. An open interval is just a subset of the line R1, where x is between two numbers, not including the endpoints. Here we're talking about the plane. Let's say we have a and b here on the x-axis, c and d here on the y-axis, and the open rectangle is going to be anything where x is between a and b and y is between c and d. Now, when we're talking about this theorem, then think about the phase plane where we plot directional fields. Okay, so when we do a directional field, we make x the horizontal axis, y the vertical axis. We have a whole bunch of arrows, right? Okay, and what this theorem is telling me is that as long as I look in this box, stay in the interior of the box, as long as nothing crazy happens to the arrows. In other words, the function that tells me the slope of each area, as long as that's continuous in terms of both x and y, then I'm going to have a solution. And of course I should, because if nothing crazy is happening to the arrows, then there should be a straightforward way to just trace these arrows, draw a solution that just follows the slopes of the arrows. So that is what the first part says. Now the second part of this theorem talks about the partial derivative of f with respect to y. And if that partial derivative is continuous, then not only do we have a solution, then the solution is unique. In other words, there's no way oh, and by the way, let's see, I do need to write one more little thing right here. This open rectangle needs to include the point where we have our initial condition. So let's say on this diagram that I have right here, that my initial condition is like right here. Well, if I were to have a partial derivative with respect to y that is not continuous, then that would mean that something weird could happen where I could have like branching arrows at a particular point. So maybe something like this, which would mean that I could also have some solution. Even though it goes through this point, later on it branches away from the previous solution. Okay, now I'm not going to go into all of the proof behind this theorem, but you should know that as long as we have a continuous function f, and it has a continuous partial derivative with respect to y, then solutions exist and are unique on an open rectangle that contains that. So let's use this theorem in some examples. Here is my first example. Y prime minus x over sine of x times y equals 0. Okay, this different, oh, and let's see, let's get our, let's say y of 1 equals 2. Now this differential equation is pretty, it's pretty easy to get into this form with y prime just on one side, because we can just move this other term over here. So this whole thing right here, this is our function, our multivariable function f that we're worried about in the theorem. Okay? Now, this function is continuous as long as sine of x does not equal 0. So we can say that this is continuous for x not equal to let's see, it can't be 0, it can't be the next place that sine of x is 0 is pi, and it can't be negative pi. Any integer multiple of pi makes this function discontinuous. And so that means when I look at The phase plane, x in the horizontal direction, y in the vertical direction. The places that I'm worried about are 0, pi, 2 pi, negative pi. And each one of these regions on here is an open rectangle. I forgot to mention that A and B and C and D in the definition of an open rectangle can be negative infinity or positive infinity. So this is actually the open rectangle that I'm worried about here, because this is the one that contains the initial condition. 1 is less than pi. 1 is somewhere like right here. And so let's see, up here maybe is the point 1, 2. So I can take this initial value problem and guarantee that there exists a solution from x, as long as x is between 0 and pi. Notice that since y, no value of y can affect the continuity of f, I really don't need to word this as a as an open rectangle. I can say a solution exists for x from 0 to pi. Okay? I could include y from negative infinity to infinity, but that's not really, I mean, that's just redundant information, right? So let's see. That is existence. Let's look at uniqueness. Well, to look at the uniqueness of this solution, I need to take a partial derivative with respect to y. And this function right here, remember, taking a partial derivative means you're taking the derivative with respect to one of the variables of a multivariable function, treating all other variables as constants. So when I take the derivative of this with respect to y, this x over sine of x, that all just gets treated like a constant. And so my partial derivative ends up being just x over sine of x. Just treating that as like a constant coefficient of y. And that means that uniqueness happens wherever we have existence, since this is going to be discontinuous in the same places that the original function was discontinuous. And I could say a unique solution exists for x from 0 to pi. In fact, this is always true for linear differential equations. If you have a linear equation, then your y is not going to have any effect on continuity. And when you take the derivative with respect to y, then all you're going to be doing is just getting rid of that y and looking at the coefficient, which will be discontinuous in the same places as the original function. Let's see what happens when I take a nonlinear differential equation. So let's say I had y squared y prime minus 9y prime equals x over x squared minus 4. Okay? So remember, to apply this theorem, we first need to rewrite the equation so that y prime is isolated on one side, so that we know what function f we're dealing with. Let's see. I can factor out a y prime from this left-hand side and then divide both sides by y squared minus 9 to get this. Okay, and let's see. I could also rewrite this by factoring each of these, and that's useful for this type of problem. Okay, just using the difference of squares, factoring there. So this means that solutions for this problem only exist as long as y does not equal plus or minus 3 and x does not equal plus or minus 2. And the open rectangle where I can guarantee existence is going to depend on where my initial condition is. So if x is between -2 and 2, and x naught is between -2 and 2, and y naught is between -3 and 3, then I would be talking about this open rectangle. But say x was bigger than 2 and y was less than -3, then I would be looking at the open rectangle over here that stretches off to positive infinity in the x direction and negative infinity in the y direction. So there's 9 total open rectangles that I could guarantee existence in, and the one that I would use for this particular example would depend on where my initial condition is. Now let's take a look at uniqueness. For uniqueness, we would have to take the derivative with respect to y of f. And if we do that in this case, let's see, I could just treat all of this x stuff as a constant, and then take the derivative of the rest with respect to y, and it's going to look like that. Yep. Now let's see. This happens to have, even though I have a y squared minus 9 squared now, the discontinuities for this function for f sub y are at the same places that we had before. X squared minus 4 still is 0 when x equals plus or minus 2. Y squared minus 9 is 0 when y equals plus or minus 3. So these rectangles here, these same 9 open rectangles, when we get existence of a solution, we'll also have uniqueness. Sometimes you'll see, especially with non-homogeneous equations, you might see discontinuities for the first part in f that aren't discontinuities for f sub y. And notice that if you can't even guarantee existence at a point, why would you care about uniqueness? So even if there are more discontinuities for the existence part of this theorem, still just treat them as discontinuities for this second part, because why do you care if a solution is unique if you can't even guarantee that it exists? Anyway, this should be plenty for you to do the homework. It's not too long. Mostly it just amounts to finding discontinuities for functions, and then seeing how big of an interval you can fit the solution in. So good luck on the homework, and I'll see you later.